Hi everyone, I'm Harsh. So this is a work, SNAP, efficient extraction of private property is with poisoning. This is a joint work done with my colleagues from Northeastern, Google, and ET at Zurich. So in the past 5 years, we have seen a long line of work where researchers have tried to design attacks to understand privacy leakage in trained machine learning models. This is an important problem to look at because in the current scenario, many organizations collect data from their users to train their model. And if these attacks are successful, this would lead to privacy leakage of the underlying users. So the most common types of privacy attacks you'll see in the literature are membership inference attacks, attribute inference attacks, and property inference attacks. In fact, in the past year itself, we have seen that if you manipulate a small fraction of the training data, which is also called as data poisoning, the models trained on this poison data actually amplify the privacy leakage of the users. So what threat model do we focus on? We focus on the property inference threat model with poisoning. So in the property inference threat model, the adversary is interested in extracting global properties of the training data set from a model. So say an organization collected data from its user, and the adversary is interested in knowing what fraction of the people have lung cancer. So the adversary starts with creating a poison data and attaching it to the training data set. The organization then trains a target model on this training data and provides a black box access to the adversary. The adversary can query this black box model and get back predictions. Usually predictions are one of two forms. That is, either you get back model confidences, which is the probabilities on each class label, or you get just the predicted label itself. We provide attacks for both versions, but for the purposes of this presentation, I'll focus on the model confidence version. Usually the success of the adversary is measured by a distinguishing test between two fractions of the target property. So say for this particular example, the adversary is interested in knowing is 0.1 or 0.4 fraction of the people have lung cancer. So how did previous work try to tackle this problem? They proposed a metaclassifier-based approach to predict this target fraction. However, in order to train this metaclassifier, you internally are required to train hundreds of shadow models, which makes this approach computationally expensive. And additionally, we observed that they required large poisoning rates for the attack accuracy to be high. So how do we circumvent these limitations? So we propose a new property inference attack called SNAP, which has a much higher attack accuracy, is much faster, and requires much less poisoning than the prior work. We additionally provide a theoretical framework which explains the effectiveness of our attack. We provide 3 different extensions. The first is the label-only attack, which is where the target model just gives you the predicted label. The second is the property existence attack, where the adversary is interested in knowing if the property is even present in the data set or not. And the third is the size estimation, where the adversary is interested in knowing the exact size of the property. We evaluate our attack over 18 different properties and observe that our attack accuracy is pretty high at very low poisoning rates. Our attack is divided into 3 main phases: the data poisoning phase, the model confidence learning phase, and the distinguishing test. So before I discuss each of the phase in detail, I'll first discuss the insights that we have for our attack. So say we were interested in knowing if the model was trained on T0 fraction of the data or T1 fraction of the data. We observe that if we don't poison the data set, then a model that was trained on T0 fraction of the data and another model that was trained on T1 fraction of the data, if we query both of these models, the distribution of the model confidences turned out to be very similar, and they overlap with each other, creating no separation. But when we introduce poisoning, the two distributions get impacted differently. In fact, when we increase the poisoning rate, we observe that the distribution for the smaller fraction gets impacted more because the model trained on this fraction has a higher misclassification rate. So now, given this confidence separation we have here, we can use it as a distinguishing tool, a tool for our distinguishing test. Till now, I haven't explained what kind of poisoning attack we use. We are using a version of subpopulation poisoning attack where we define the subpopulation to be as our target property. You can find the details of this poisoning attack in our paper. Additionally, we also provide a theoretical analysis for this confidence separation, which also you can find in our paper. So in our second stage, which is the model confidence learning stage, the adversary starts with training k shadow models per fraction. Once these models are trained, the adversary queries all the models and gets a set of confidences. After getting these confidences, the adversary fits two Gaussians on the distributions and finds a threshold that will separate the two. So recall that in the previous work, because you had to train a meta-classifier, you required thousands of shadow models to be trained internally for the distinguishing test to work. Whereas, because we directly use these model confidences to build our distinguishing test, we require no more than 8 shadow models to be trained, making our attack really efficient. So the final stage, which is the distinguishing test, the adversary gets black box access to this target model. The adversary queries the target model and gets back a set of confidences. So after getting these set of confidences, the adversary checks if the majority of these confidences fall to one side of the threshold, then it will predict it as fraction T1, or it will say it's fraction T0. We also additionally provide analysis on how many queries do we really need for the adversary to succeed this test. You can find this in our paper as well. So we have several extensions in our paper, but I'll focus on the size estimation extension. So this is a very realistic threat model, as the adversary may not always have information about the exact target fraction T star. So the crucial observation we make here in the size estimation is that the distributions follow a strict size ordering. So what do I mean by that? Say a model was trained on fraction T0, then the distribution, then any other models that were trained on fractions that were greater than T0 for the same target property will have their distributions on the left-hand side of T0, as shown in the figure here. So now, given this size ordering, we can now exploit a binary search-based approach to compute the target fraction T star. So previous approaches have tried tackling this problem, but required close to 20,000 shadow models to get an accurate estimation. But because of our crucial observation here, we can exponentially drop the number of shadow models that are required to train to not more than 14 models here to get an accurate estimation. So let's look at the evaluation phase of our work. We try our attack on 4 different data sets over 18 different target properties, which are categorized into 3 broad categories. The first is the large size, then this medium size and small sized. We try over different versions of feed-forward neural networks and a convolutional neural network, ResNet 18. We check what the attack accuracy is, that is the adversary able to correctly distinguish the fraction of the target property? And finally, the execution time, that is the end-to-end running time to mount the attack. So here we observe that as we increase the poisoning rate, the attack accuracy improves much quickly. And here each plot shows the large target property being attacked. And we additionally observe that we require only 5% of poisoning to get our attack accuracy greater than 90% for almost all the properties we tested here. In fact, for the medium properties, we require no more than 0.6% poisoning to get very high attack accuracy. We have several extensions. Here I'll discuss about the property existence. Recall that property existence is where the adversary is interested in knowing if the property was even present in the data set or not. Here we observe that for property existence, we required no more than 8 samples to get an attack accuracy of greater than 90%. Similarly, for property size estimations, we got accurate estimations at very low poisoning rates. So how does our attack compare empirically against the state of the art? We saw that our attack has a 34% higher attack accuracy than previous work. We are 56 times faster while requiring 4 to 6 times less poisoning than the previous work. In fact, even in the label-only version of our attack, we consistently outperform previous work while having the same efficiency benefits as our confidence attack. So in conclusion, we propose a novel property inference attack that is much more efficient, requires much less poisoning, and has much higher attack accuracy than previous work. We provide a theoretical framework to explain why our attack is so effective. We extend our attacks for the label-only setting, the property existence and property size estimation versions. Defending against property inference attack is still a hard problem to solve. We empirically evaluated and showed that differential privacy is not enough to prevent property inference attacks. Thank you. I'm happy to take any questions. And this is the QR code if you want to run our attack.
Thank you so much, Harsh, for your presentation.
Nice talk. I actually have 2 questions. The first one is a very simple detail one. So is your poisoning attack a clean label attack or dirty label attack? And the second one is that, as you mentioned, there is no, the defense against property inference attack may be an open issue, but there are many defenses to detect poisoning attacks. So is your poisoning data like susceptible to those detections? Thank you.
So to answer your first question, no, ours is not a clean label. It's basically a label flipping strategy we are using from the subpopulation poisoning paper. And secondly, so here we did not test on detecting data poisoning specifically because we really needed like very small fraction of the data to be poisoned. So yeah, we were directly testing on defenses that would try to mitigate property inference rather than, say, detecting data poisoning specifically. Yeah.
So my question about the practicality of the attack, I mean, you mentioned efficiency in terms of time and number of models, the shadow models that you need to train. But is it practical to poison 5%, even though it seems, I mean, you're talking about hundreds of thousands, especially for big models. I mean, that percentage is still high, and I don't think that is practical to poison.
So in fact, so that's why we had medium properties also, which required like 0.5 to 0.6% poisoning. And practicality in the sense that you do collect data from a lot of users. So you can, in fact, manipulate a fraction of the data. But in terms of just the size itself is what you're wondering. We do also, like if you look into our paper, we have an optimized version where we'll actually show that you can further reduce the poisoning rate to 1 to like less than 1% to 1%, even for larger properties. So in that sense, I think like if you are able to manipulate 1% of the poisoning, that should be a good enough. I think it's a reasonable thing to have, I guess.
When your attack is trying to estimate the distribution of some property, is your attack outputting from like a continuous, array of possible percentages, or are you just choosing from some limited number of percentages or buckets of percentages?
Do you mean for the size estimation?
Yes, for the size estimation.
When I have to estimate. So basically try to, so based on the binary search, we try to come close to it and see if the distribution, so the attacker keeps guessing every single time and sees if the distribution of his guess is it overlapping with the target model's distribution. And then so you can have various stopping conditions there. So one of the stopping conditions we had was we were seeing if the overlap of the minimum confidence that for the attacker's guess distribution, is there a significant overlap between the two? And that's where we stop. And we saw that we had like really close actually approximation to the original target fraction value.